We're going to look back today, back to chapter 3, and we're going to start with a question that was one that we looked at back in chapter 3. And here we are in chapter 27, and there's a concept we're going to revisit, and the concept is relativity. First, back to chapter 3, for Galilean relativity. Now here's the question. There are 4 people. There's Amy, there's Carlos, there's Bill, and then there's someone who's running. Amy's standing still on the ground. Bill is riding a bicycle at 5 meters per second with respect to Amy. There's a runner moving at 5 meters per second with respect to Amy, and Carlos is driving in a car at 15 meters per second with respect to Amy. Here's the question. How fast is Carlos moving from Bill's point of view? So from Bill's perspective, from Bill's frame of reference, how fast is Carlos moving? We'll give you some choices. Now this is a concept you looked at back in chapter 3, and we saw an equation for solving problems like this. And when we did this, you can see that the velocity of Carlos relative to Bill is 10 meters per second, because Bill is moving to the right at 5 meters per second. Carlos is moving to the right at 15 meters per second. From Bill's point of view, Carlos is moving away from him at 10 meters per second. This is a concept known as Galilean relativity, and it makes sense. It makes nice, intuitive sense. But things are different when we're moving at speeds that approach the speed of light. So now we're going to move into the realm of special relativity, and we're going to look at a similar problem, but with a difference. Everything's moving much faster. So now, suppose we have this. There's a light beam which is traveling through space, and 3 people are chasing it in spaceships. And they're chasing it at speeds that are a fraction of the speed of light, either a quarter of the speed of light, or a half the speed of light, or 3/4 of the speed of light. And then someone is standing still, watching the whole scene play out. Here's a question. From the point of view of the person who's moving at half the speed of light, how fast is the beam of light moving away from her? What is the speed of the beam of light relative to the person in the spaceship that's moving at half the speed of light? We'll give you some choices. Now this is a result which is truly surprising, and the answer is this. The light beam moves away from her at the speed of light. As a matter of fact, for any of the people who are traveling after the beam of light, or the person who's standing still with respect to the beam of light moves at exactly the same speed, the speed of light. So when I have my laser pointer, if I shine this on my hand, it moves from the laser pointer to my hand at the speed of light. But if I was shining it toward a car, and someone was looking at the rearview mirror, and watching the beam come towards them, it would move towards them at the speed of light. Or if I shine the beam and I chase it, no matter how fast I travel, it moves away from me at exactly the same speed. The speed of light is a constant, irrespective of the motion of the observer. And because that's true, something else very, very bizarre has to happen. We've got to play games with space and with time. And now we're going to do a thought experiment. Here's our thought experiment. Suppose there were 2 versions of me, and we met in the studio, and both of us synchronized our watches at exactly 9 o'clock. And then, one version of me went off on a fast spaceship at 95% of the speed of light for 1 hour from the point of view of the version of me that stayed behind. We come back together in the studio, and we compare watches. The one who stayed behind sees that it's 10 o'clock, exactly 1 hour has passed. The one who's gone off at 95% of the speed of light measures a time of about 20 minutes. So his watch is measuring 9:20. And the difference is not something that happened to the watches. The difference is something that happened to time. The version of me that was moving at 95% of the speed of light experienced a smaller passage of time. We have a treatment in the book that explains this concept of time dilation, that things moving at different speeds will experience different passings of time. It's a crazy, crazy concept, but it's true. And not only do you have to play games with time, you have to play games with space. We'll see in the book that there's something called time dilation, but there's also something called length contraction. And the fact that space and time are relative to the motion of an observer comes about because there's one thing which doesn't change with the motion of the observer, and that is the speed of light.